Thanks, Sunil. Thanks a lot. So welcome, everybody. Thank you for giving me this opportunity to give you some new thoughts. Maybe old, maybe no. You see here, I used the font of GlobeCom the first time. This is the title of my talk, and I'll be talking about where are we right now, and what should we be thinking about when we go forward. I mean, if you look at this kind of a Huawei vision, yes? I'm scared. Why would we need 0.1 millisecond air interface? Battery life of 20 years, everybody would love that. But there are many, many question marks here, and why are there the question marks? Well, let's have a look at the stock market, because there the question marks come from. We have a wireless industry. We're excited about our wireless industry. And let's look at the S&P 500 of the last years. This is the latest data of last Friday. So I checked the stock market on Friday, and these are all the numbers of last Friday. So we have a cumulative average growth rate, a CAGR, of around 10% of the long run. We have had a nice run before, even though we've had Putin's war, financial crisis, Y2K aftermath, everything there. But still, we've seen sort of this nice long-range 10% CAGR, which is CAGR, which is about what you see since 1928, for the last 100 years. But what happened to the operators? Let's look at some examples. In Asia, the only operator that I'd picked is China Mobile, sorry. In Europe, Telefonica, Vodafone. In the US, AT&T, Verizon. And I chose Deutsche Telecom, which has operations in Europe and the US. So let's have a look at it. Over the last 5 years, things look okay if you're a Deutsche Telekom stock shareholder, because you met the S&P 500. China Mobile, nyack. And the others, really bad. And this is the latest data of last Friday. If we look at 10 years, okay, the S&P 500 should be at 254%. Actually, Telecom is only at 150%, and the others are bad. If you go to 15 years, it's even worse, and if you go to 20 years, it's really bad. So our industry has not been successful in monetizing not 5G, but 4G and 3G as well. Okay, if we look at then as I say, the CAGRs, here the 20-year, here the 10-year CAGR, really bad. So it's really understandable why NGMN came up with this new paper. We're co-author of the new vision paper in October this year, which says the telecom industry has reached an inflection point such that it can no longer be automatically assumed that a new radio access technology would inherently add value in a 6G system. My goodness, what does that mean? It also says, for a new 6G radio interface to truly add value when compared with the most advanced capabilities of 5G, improvements that make a meaningful difference are needed, reducing network cost, while also improving customer experience and generating revenue growth. So there's an outcry of the operators, please help. And we are here, we must answer this outcry. Then let's go to the suppliers. Let's say the suppliers are doing better. Yes, we've had quite a few suppliers that has been shaken down to just Ericsson, Nokia, Samsung, and Huawei is private. So no data really that we can take on Huawei's share price. And we can take Jeff's newest view. He says, we believe the 5G PHY will not be wholesale or even significantly replaced by the 6G neural network for two main reasons. And the new reasons are not neural network reasons. He says, we're basically there. 5G is near optimal, and it's really efficient to implement. So, guys, there's no future if I read this. Look at Nokia's talk yesterday. The overall 6G design principle, aiming for lean system design. Look at this. Where's the vision? Where's the beef? 6G RAN study should aim for lean system design. Lean system, where's the new revenue opportunity in a lean system? Just says the standard should be simple. That's what all this text says. Let's look at what happens. Yes, the last 5 years, Nokia, Ericsson, Samsung, the S&P 500 was 101% up, Nokia 21%, Ericsson -6%, Samsung -10%. Then let's look 10 years. Samsung looks better because of its phone business. I took Samsung as a whole company. And 15 years, 20 years, okay. So the only one that seems to be hitting this is Samsung, but not because of its infrastructure, but because of its consumer products and because of semiconductor. Ericsson over the last 20 years has been -42%, Nokia -72.5%. That's not value creation. Yes, and if we look at the CAGRs, not really good over the 10 last years and over the 20 last years. So what else do we have to think about? We have something else to think about. This is COVID. It's been an idea pause, because look, this is the US patent filings. And if you take a look at this, you see in 2017 we ran out of steam already before COVID. And then we had COVID, and we had Putin's war. So now we assume we can still continue as usual, even though we have had 3 years of idea pause. And if you look at the European filings and the details, looks pretty much similar. It's flattened out over the last years. And if you look at my own startup history, we've created 19 startups so far. 1999, 2000, 2003, 4, 5, 6, et cetera, almost every year, except 2009 came the financial crisis. Boom, there were 3 years of pause. And then 2017 to 23, you see again, our startups have been drying out. Good news is I have 5 teams working on startups as we're speaking. And so there's 5 teams in the makings right now. So that's what I'm trying to tell you. There's hope if we address it in the right way. So let's think back. NGM said we must reduce network cost, improve customer experience, generate revenue growth. But my thoughts is on standardization, we should also take a 3-year break. Even the release numbers has slowed down. We used to have a release every year. That hasn't been happening in 3GPP. So it's time to take a break to generate great ideas, because I have the feeling the coffers are full. If I look at the faces here and many people in my team and then other people I meet, we're getting ready to fill the coffers. But if we start standardizing now, we just come to the same conclusion that Jeff came to. He's lost. Where are the ideas? So let's have a look at what can we learn from 5G. We can learn from 5G, we can do teleoperations. This is new. We can do it all over. We can do it here. These are different teleoperations, MPNs that we've done in the Lausitz, we've done in the fields, in the crops, in the vineyards, in the orchards, etc. We're in the Leipzig airport with DHL's hub and all these different test beds. And we're building right now a 100 times 100 meter 40-meter tall hall where you can try out all these different applications, use cases. So we have had 200 use cases that we've examined with my team, running all these MPNs, and with more than 50 companies participating from all kinds of different vertical industries. Flying drones, driving cars, in the hospital, in the factory hall, logistics, whatever you call it. What do we learn? Some learnings is that my good old roadmap seems to still be true. Meaning that we've had 2 generations of voice, 2 generations of data, and we need 2 generations of mobile. Why do I say this? The first generation addresses business customers, and we whet the appetite for consumers, giving them something cheap, ISM-based, for free, cordless phones. That's good enough. No, it's not good enough. Once we put 2G, it really makes it happen. Then we say, oh, mobile internet is the really cool thing. No, it is not. It's just for business customers. It's just Nokia, Communicator, BlackBerry. Not that great for consumers. But we gave consumers Wi-Fi and the laptops. Again, ISM band. But then with 4G, we shrunk the laptop into this handheld, and off it went as a consumer device. If you think of all the examples I showed on the previous slides, it all addresses business customers. All the 200 use cases, all the 50 verticals plus. It's all business customers, not a single one doing ultra-reliable, low-latency communication for a consumer. But we're not only addressing mobile robotics with URLLC, we're also doing this with Wi-Fi. So things are happening in Wi-Fi. We're connecting our lawnmowers, our vacuum cleaners, doing XR experiences. So once we have 6G ready, and 6G addresses really the personal mobile robotics, we're going to have a road rocking full of ideas. Another key learning. What did we learn from that roadmap? It's not only introducing certain use cases first for business customers, then consumers. We engineers also do the same. CDMA was first in Wi-Fi, then in 2G. OFDM first in Wi-Fi, then in 4G. MIMO first in Wi-Fi, then in 3G. LDPC first in Wi-Fi, then in 4G. Millimeter wave first in Wi-Fi, failed big time, then in 5G, not doing great either. So there's no good rule, of course, without an exception. So OFDMA, yes, that was first in cellular, then in Wi-Fi. So what we see, however, is maybe we should rethink what we're doing and also concentrate on something that we've lost interest in, meaning Wi-Fi. Let's have a look. An example where this really is super important to first think Wi-Fi, then cellular. Reconfigurable intelligent surfaces. Everybody, I've seen so many papers publishing that under the narrowband assumption. If you look at an RIS, it is not a narrowband system. If it's not a narrowband system, we get grating, we get squinting, we get frequency-dependent beam width, we get all kinds of dirt effects. You think you're pointing this way, you're actually pointing that way, because your coefficients are set for a different center frequency. Another issue. In cellular, an operator is allowed to use an RIS that operates in its band. Now, every cellular operator has multiple different discontinuous bands, and you're not allowed to emit anything outside your license band. Tell me how you can do that with the current RIS technology. Another problem, or not a problem, I mean, if I put up an RIS, I need power. If I have power outside, it's easy to put in fiber as well. With power comes fiber. If I have to lay power, I lay fiber. So why not just put up a small base station? Much simpler, cheaper, better, under control. Then the control channels, still a big challenge going ahead. How do you set up this kind of RIS? With beam tracking, interference control, and we have to do twofold beam search, yes? We have to look at the incoming and outgoing beam. Then another issue with RIS, which often is forgotten, we operate the RIS in the near field. In the near field, a phase control of the beams make no sense. Because in the near field, I actually have to look at a focal point and not a beam. And I have a focal point, angular as well as in distance, a focal point. So just setting coefficients is not going to manage that. And the focal point is frequency dependent. Further issue, we have inner symbol interference that is never addressed in RIS. Yes, we have multiple symbols popping in, and they're actually, as they're popping in, the next symbol is hitting the one edge of the antenna array as the old symbol is still leaving. So this is yet an issue where, again, the performance of RIS is degraded big time. We know this from massive MIMO antennas in 3.5 gigs that are currently being sold. They all have true time delay circuits in there to address this. They don't do phase shifters. But there's a huge opportunity. Let's make it happen at Wi-Fi. Because at Wi-Fi at 60 gigs, we have 1 gig of bandwidth. And if you look at the numbers, we can operate RIS in a narrowband sense and make all these problems go away. And we actually have beams. So, and if we get it to work in the 60 gigs ISM band, that would be great. Then finally, this could be a breakthrough for millimeter wave to make sense in the ISM band. And then we can learn a lot and then apply this also for cellular. So let's talk about another issue. What do we want to do? We want to get the cost down. That's what the operators say. Right now, they spend 20 to 40% of their OPEX, of their operational expenditures, for energy bill. I'd rather take 10% of that, yes, 2 to 4% of the OPEX, and have them invest into silicon, into ideas where our IP is, our patents, our innovation is in there, and cut the energy big time. Why are we wasting all our smarts in making just the utility companies happy? That's not generating jobs. That's not generating value. So let's give you some new updates on my gearbox idea. We see here, this is an NGMN study. If we look at other RANs, you see it's even worse. We see that we have about 2/3 of our energy utility bill goes into the radio part, in the actual radio transmission. 75% if you take baseband and everything in there. So now the question is, how do we get this thing to work? And if we look at how data happens in time, over area, we see it's fragmented. It's not uniform. It's not a hexagonal network that we need to address this kind of a cellular data. We build a model, and here you can see nice in the animation how this happens over time, yes? Over 24 hours, data hotspot pop up here because of homes, there because of offices, and then over time, they move around. So you can build these kind of models and actually make them happen and understand and build a network to address this. What does that mean? If you look at that, most of the area is flat, very dark. For us, that means the distribution of data rates is with very high probability, we have low data rates. With small probability, we have mid data rates. And with very low probability, we have high data rates. Yes, the chances of really needing a full buffer maximum kind of data rate, as we publish a lot, me too, I've done that a lot, is nearly 0. Yes, 10 to the minus 4 is the assumption. Not in space, but in space-time buckets, yes? So if that is the case, look here, this is what Nokia has measured. They measure the same. So what does that mean? We have available spectrum. We have a lot of available spectrum. Our spectrum is not congested. It's typically, I mean, if we are in a congested situation, we have about 2 bits per second per hertz. Maybe even 0.5 bits per second per hertz, if we take the countryside in addition. So we have very, very high available spectrum, a lot of high available spectrum, most of the cases, and we only need this crunch, NOMA, or whatever you call it, in very seldom cases. That means in these seldom cases, it's okay to eat enough power, 100 times more power for the new 6G, if it just is turned on very seldom. 10 to the minus 4, that means we still get it 100 times. Similar, we can do this argument, and so the idea is we want to get 100x power savings by just turning on the right gear at the right time. That means, yes, we have to put in hardware transceivers next to each other. Like a quadrature amplitude modulation hardware receiver, a zero crossing modem, and an impulse radio. Let's take these 3. Right now, cellular only does the red, even though the blue and the green hardly uses any silicon area. Now you have to look at all the different components that are needed in the whole transceiver chain. If you use Shannon, you're toast. because Shannon doesn't tell you the total energy consumption. Shannon just tells you SNR capacity. We really have to look at the energy consumption because the phase noise that you can allow with an impulse radio is much higher than in an OFDM transceiver. So the whole idea, and this means you can also use components that eat much less power. Often forgotten, if you just look at Shannon formula, you don't see that. You really have to build the RF transceiver system and the A to D converter part. And then you basically do some mathematical optimization, understand the whole model. And this is an example of what happens if you were to do this in millimeter wave. So in millimeter wave radio, it turns out at 60 gigs, up to data rates of 500 megabit per second, impulse radio, the green line, is a couple orders of magnitude lower energy than OFDM, which is the purple line, what we do now, single gear QAM, the purple line. And then there's some area where zero crossing modulation makes a lot of sense. So let's turn on and zero crossing modulation takes us all the way to data rates of 10 gigabit per second. And look at the Y-gig standard, OFDM, or single carrier QAM. What a waste of energy. No wonder Y-gig doesn't work from a market point of view. Of course, this is different depending upon which frequency range you use, and we still are doing all our analysis with RF transceiver designs and all this thing, and we're improving this over time. This is where we are now, and this assumes that we do allow duty cycling, and we can instantaneously turn on a QAM transceiver and turn it off with a duty cycling of like 10 to the minus 6, which is, of course, impossible. So these numbers here are still very much to the benefit of QAM. But the gearbox gets all these benefits. You see up to 3 orders of magnitude of energy efficiency. So that means we had an energy issue in 1G. If you look at the clunky radio, we invented something new as a community addressing that. We thought this is so great, but then that we can use it for 3G. What a mistake 3G was from an energy point of view. Yes, remember the BlackBerries where you turned off 3G and turned on Edge because otherwise the battery was drained? Then we came up with OFDM, addressing the energy issue. Great. Then we thought OFDM so great, we just use it for 5G again. Maybe it is the right thing to use, but maybe only as a gear for 6G, as one of multiple opportunities in the gearbox, as I propose here, but I mean, there are other proposals that you certainly can come up with, so that we really focus on building cellular networks where you can earn money by not wasting all that energy. Then let's look at consumer robotics. What do we have? The green ones are what NGMN says, so we need affordable personal mobile robotics for new business cases. We need the energy down, we need new functionality. Let's have a look at AML. I'll just skip through these slides quickly. What is the issue with AI/ML? Why do we have an issue? The issue is not because we use algebra. This is algebra with 2 operators. We know it forms a semigroup. All is great. We can do matrices, and we love this. But there are other examples. Look, and there are nonlinearities, but they're linear in this semi-ring algebra. Then we take this to 3 operators, and it turns out it's linear. So what is the problem with AI/ML? The AI/ML problem is it is linear algebraically, but not in matrices. And right now, all the algorithms are designed around using NVIDIA matrix compute power. And so if you do matrix theory over 3 operators, it fails. It's not linear anymore. This is where we have a problem. This is where we need research to find out what can be done. Now, so it is not the rectifier linear unit or some softmax or whatever you use that is the issue. It is the matrix algebra is falling apart right now. Then we have an implementation challenge because of it, because of it, we need all the data to come in there for all these matrices. We have a huge amount of reading data. Here an example of a chip project that we did together with BMW, for the ADAS, just to give an idea. Because of our new president coming in, they were anticipating that and thinking maybe Qualcomm cannot provide the chips anymore. So it's a typical kind of architecture. No, it's not. It's a serial bit plane architecture, and that makes it different. By doing so, we can actually address all the addressing problems for memory fetching with dilated convolutions, with different quantization stages, etc. And these are the partners. This is the chip. And what do we get? What did we do? When BMW approached me 5 years ago, I said, "You're crazy. Me designing an AI/ML processor?" They said, "Well, it's single processing. You've done so many single processing chips. Why not do it?" Yes, we did it. We're better in teraops per square millimeter. We're better in TOPS per watt. And we're better in this measure, which is sort of the combined measure, than the state of the art right now. That's the MediaTek chip that we're comparing. So yes, that is what we can do. But last not least, what is it that we want to talk about? It's about trust and trustworthiness. We trust each other when we walk into a crowd of people. If we talk about personal mobile robotics, we have to trust them that we rather go to a robot to be vaccinated than having a medical doctor do that. That's the level of trustworthiness that we have to have to machines, to moving machines. Why is that so important? Look what happened to these guys. The hottest stock on planet Earth, and then it crashed. Why did it crash? Because it physically impaired a child that was killed by the pedals. That was the first little dip. But the real dip was when Hollywood came up with this sequel where they came up with the idea that somebody hacked into the system and the other guy was on the peloton and got a heart attack because the way they played with him. It's just a movie script. It's not reality. But just the fact that people are scared once we have physical objects means we have to start thinking. So we can start thinking going back to Luhmann or to Meyer. So that the two big pillars in research and trustworthiness in social sciences. And here is Meyer's model, and you see something here. There are factors for perceived trustworthiness, and then there's trust. He differentiates between trustworthiness and trust. And as you see, factors of perceived trustworthiness and perceived risk is trust. So trust is something subjective, and the other one is objective. We took these perceived factors, we call them characteristics, confidentiality, integrity, accountability, authentication, privacy, applied this to 5G and O-RAN, did a study for the German Cyber Agency, and what is the result? The result is this. We can hack into the system all over the place, and in the plus, we even know how. Because we build systems for functionality, not for trustworthiness. This is a study we did of the Backhausen Institute for the German Cyber Agency. We published a paper, and a couple months later, also there was a standard on trustworthiness. Trustworthiness is an attribute that can be applied to services, products, technology, data, information, as well as organizations. And it is defined over measurable characteristics that you can measure objectively. Okay, so let's try to build a model. So we have objective characteristics of trustworthiness, privacy, security, integrity, resilience, da-da-da-da-da. We can measure these. We can say this is what it is. And then, subjectively, we are in the center lane of a 3-lane highway, and we decide subjectively, do we take the left or the right lane to pass the car in front of us? This is assumed risk, perception, situation, competency of me, of my car, and of course, experience. But there are also mediators, because I know this car has been certified. It's from this kind of a quality company, so there are certifier auditors, agencies that so I don't have to check on all that myself. And then I take action, and this is subjective, not objective. I trust that I can take this action, and then I learn from the results. We put this out on archive. We've submitted this to a journal, put this out on archive already. We want to get the discussion going. The discussion going on, we engineers have to address this topic of trustworthiness. Why? Because if 6G is really going to give us new services, I truly believe it's personal mobile robotics, the exoskeleton, the automated driving car, the whatever all. And we really have to make sure that we build these systems ground up from trust. We need a processor that we can fully trust, that is certified, measurable. We need an operating system that interlinks with the processor, not like taking a Microsoft operating system and Intel CPU. We need a software system sitting on there. And we, of course, have to address the most vulnerable interface, which is the air interface. The additional thing that we need is we have to look at the system. Systems are designed with components. What is the issue with ORAN? It's the XApp interface. The XApp interface is super nice. But the XApp interface, as it is implemented, I don't say in general, but as it is implemented, allows you to fiddle with every single component and mess it up. Meaning interfere with it. Embed your own stuff. And so we have to not only look at how to verify components, but also how to design interfaces so that we don't make the mistake that we made in ORAN. So we need trustworthiness by design with integrity control. Now, if you look at 3GPP today, how do you know that the variable on page 17 is the same as in 4397? So how do you make sure that this thing has integrity, that it has formal specification and formal verification? So we design today for functionality. Tomorrow, we have to design for trustworthiness by design. It's like designing a car. It used to be a carriage with a motor and just to function to go from A to B. Today, you already think of crash zones, safety belts, airbags, all these things, right there at the beginning of design. And the bottom-up trustworthiness technology has to be there. We need platform chips with operating systems that really are trustworthy, methodologies and architecture, and our wireless interfaces. There's our wireless stuff. And we address all three. That's exactly the reason why I started the Backhausen Institute. And we're 100 people working exactly on this topic, and I would like to have 9,000 people working on this topic worldwide, not under me. Don't worry. We address this in the medical field, together with the medical electronics and the medical health. So Jochen Hampe, who is the head of internal medicine, and me, we head this whole, it's about a €100 million program. We're trying to do this for medical already, because medical devices are much smaller than networks. So in conclusions, here are some platform chips we've designed over the years with my team. These are the last two that we designed last year. Yes, the left is our ADAS chip. The right is our trustworthy compute platform chip. Left from the university team, right from the Backhausen team. Now it's time to combine the two. And what else? We see a appetite for more data. So we need to address the energy problem, because we see a huge drive for high bandwidth memories today because of AI ML. Tomorrow we'll have distributed AI, because we want trustworthy islands where I do my local compute in a trustworthy AI accelerator, interacting with the cloud AI engine, and that data traffic between the terminal and the infrastructure is going to be huge. That is where the growth in data is, I truly believe. And that is going to make this wireless roadmap look like peanuts. So we need to be designing these low-cost 6G system design, low power, with trustworthiness from ground up. We need to reduce the network cost, improve customer experience, generate revenue growth, the 3 bullets of the NGMN paper, and not forget to take a break in standardization. I think we need at least 3 years break, shift out the 6G standard, because there's so many ideas. Look, if I talk to people luring around, they're just waiting to be captured, but if we start standardizing, we're just going to be at the crossroad now. Meaning, if we standardize too early, it's a standard that the stock market is not going to accept, and it can kill our industry. Look at the stock performance already. We don't want this to have another minus 3 dB drive down. Thank you.
Thanks, Gerhard. In interest of time, I can take one question. Anybody has one burning question? Seems like everybody understood everything very well, Gerhard. Okay, well, we can take the, yes, please go ahead, Prof. Lin.
Yes, I was just running to the nearest mic. I'll try to make it short. So the question is, or it relates to your idea of pausing for 3 years, 4 years, 5 years with the ideas, and I couldn't agree less, right? But maybe the problem with the technology innovations comes from the problem with goals alignment. And as of today, as some can observe the standardization process, there is a big misalignment. As a community, we want a clean, efficient, compact specification, which is easy to implement, so it's cost efficient as well. As an individual contributor, I want my patented innovation inside the standard, which means that the spec will be very much overcomplicated in the end. Would you agree, and if not, why? And if you agree, how could we fix that? Thank you.
I truly think the people running the stock market are not stupid. And I truly think they're not going to allow for an operator to invest in 6G rollout if it just doesn't give you any benefit. Yes, so if the CapEx is not changing, or a CapEx is increased because of a dramatic decrease in OpEx, that's fine. So I think the days are over where we just have the stock market accept that we need the next standard. I think we're at an inflection point where we really have to make sure to address this issue. Otherwise, yes, I understand your problem, but the CEOs of our companies are talking to the market daily, and they have to make sure they address that, and they're going to call us into reasoning, I think, sooner or later.
Thank you very much.